Hey guys, Mr. Lawrence here. Sorry I'm not in class today. I had to go to the doctor with my wife. We're pumped. We get to find out the gender of our baby. So we're really excited, but obviously I wanted to be there for that. And that happened to be during class. So what we're going to do though is you are going to go ahead and continue today without me on the lesson on effusion, diffusion, and Graham's law. This lesson is helping you understand how quick things diffuse or effuse. So as we get started, let's just remind ourselves of some vocab. Diffusion is when we have some kind of chemical that starts very small and it disperses and spreads out to the masses. Effusion is the opposite. When something is large, it's at the masses, and it comes small by going through a small opening. Both of these have the same concept. Both of these work due to the kinetic molecular theory. And so, again, remind you of what kinetic molecular theory means. It just talks about this idea that how we believe particles are in random, constant motion, and that because of that random, constant motion, things will automatically mix. And so we'll come back to this in a second. But before we do that, let's look at this little demonstration I have set up here. Here are 2 glasses of water. And so, again, we are going to look at the example of diffusion. Diffusion is this idea where if I take these 2 dots of food coloring, we should start to see a natural mixing and blending of the dyes. Now notice, I am not stirring this water at all. I am not touching it. They are just naturally moving and dispersing on their own. I wonder if I can get a light going on this real quick for you guys. That might help. See it maybe a little better. There you go. But you can see how they are naturally moving. So this is part of our kinetic molecular theory, where basically particles are always in random constant motion, always colliding, and so therefore they are spreading out by themselves through that random constant motion and those elastic collisions. So what we're talking about today, though, is how quick these guys diffuse or fuse. How quickly do they spread out? And that's what Graham's law does for us. The simple idea here is that the heavier the chemical is, the slower it diffuses. The lighter or the smaller the chemical, the quicker it diffuses. We say it again. The heavier it is, the slower it is, the faster. So think of it in this terms. Think about the game Planko that you see on The Price is Right. Planko is that game where you have those little discs and they fall through the pegboard and they go plank, 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 and then they fall on the bottle and they rattle back and forth. Well, if I had a big disc going through Planko versus a small disc going through the Planko, which one would make it through faster? A big disc has a bigger surface area and it's going to make more contact with the pegs on the way down, and it would go through slower. A small disc would just simply zip down and it might bump into a peg or 2, but it can move through that space a lot quicker. Same thing we got going on here. The larger the molecule, the heavier the molar mass, the slower it's going to diffuse or effuse. The smaller the molar mass, the quicker it can diffuse. And so what Graham's law does for us is actually allows us to calculate those rates of diffusion. So as you read through here, we see that Graham's law came up with this idea of how we can relate or how we can compare the speed in which things will diffuse based on their molar masses. And so the equation is simply the square root of their molar masses and them being compared. And so what we see here again, the key idea is that the molecule with a lower molar mass will diffuse faster. Things with a higher molar mass will diffuse slower. And so if I have a sample problem like this where it says compare the rates of effusion for hydrogen and oxygen STP, you can look at and say, okay, well, how fast will hydrogen diffuse compared to oxygen? So the equation we use for Graham's law is simply the square root of the molar mass of one chemical divided by the square root of the molar mass of the second chemical. The only key when you do this is we do want to make sure the molecule that has a higher molar mass is on top. But other than that, all we're doing is we're just finding a comparison. We're just finding a ratio here to find out who is faster and slower. So mathematically, this is pretty simple. The first thing we want to do is we want to make sure we understand what the square root button is. The square root button is the opposite of something being squared. So if I have the number 2, and I want to find it squared, I would hit that, where it simply takes 2 times 2. And then if I hit the square root button, it reverses that order of operation. So here, you're going to be finding the square root of different masses. So how did I find the molar mass of oxygen? My periodic table. How did I find the molar mass of hydrogen? My periodic table. How do I find the square root of 32? I would simply put in 32 and then hit the square root. Comes out to 5.6. How do I find the square root of hydrogen's molar mass? Type it in, take the square root, and so I get 1.4. So then to solve the problem, I take 5.6, divide by 1.4, and I get this ratio of 4. What you just calculated here is the idea that hydrogen will effuse or diffuse 4 times faster than oxygen. So simply because his square root is 4 times smaller than that, means he will diffuse 4 times faster. Let me say that again. Because hydrogen's mass is 4 times smaller by its square root, it will diffuse 4 times faster. And so all we're doing is we're just finding this ratio. We're just simply saying that hydrogen will spread out 4 times faster than oxygen. So if at the front of the room, I opened up a can of hydrogen and I open up a can of oxygen, hydrogen would empty out of that bottle 4 times faster. Hydrogen would fill the corners of our room 4 times faster than the oxygen was. So the math is pretty simple. You got lesson 41 to practice this. I'll be back in class tomorrow to answer questions. Have a great day, and I'll see you later.